In this video, we are going to walk right up to a huge rocket on the launch pad. Not only are we going to walk up to it, we're going to walk right up to the hot naughty bits. That's what I call it. We've got 2 liquid engines, 2 solid engines. They've been in development for a really long time. And not only are we going to walk right up to it, we're going to walk right up to it with the guy over the whole company that did it, Tory Bruno. Tory Bruno is a legend in the rocket community. He is extremely smart, he's an engineer by training, and he knows his stuff. Here in America, we are right in the middle of an explosion of aerospace development. There's all kinds of rockets being developed by SpaceX and Blue Origin and all these other companies, and they're making new rockets, which is awesome that we are living in an era where new rockets are being developed and they're being flown for the first time. This rocket that we're gonna see today is called the Vulcan Rocket, and this is the first time it's ever been flown. You may remember in a previous episode of Smarter Every Day, we got to see the Vulcan rocket being manufactured. In fact, these are some of the chips that came off of some of those mills that were cutting that orthogrid pattern that would ultimately become the rocket. They bump form them, they roll them, they make them into big cylinders. The rocket that we're about to see launch, we saw it being made in the factory.
Oh, those big plates that you saw machined and you saw bent and you saw anodized have to get friction stir welded together into a barrel to form an Atlas booster, or in the case of what you see over there right now is the Vulcan first flight liquid oxygen tank.
That's it. Okay, so that is the first vertical assembly of Vulcan.
Right.
And now we're going to get to see it being flown. The Vulcan rocket is especially important for ULA because they're retiring their Delta and Atlas class rockets. These are workhorses of the American launch industry, and they both have great track records of being reliable launch platforms. Yes, Tory Bruno is the CEO of United Launch Alliance, and this is the first launch of the Vulcan rocket. With all that being said, there's speculation in the industry that somebody might buy United Launch Alliance. If they do, we don't know who's going to be launching Vulcans in the future. We know Vulcan's going to persist, but we don't know what company name they'll be flying under. All that being said, I want you to understand something about Tory Bruno. He is a rocket fan through and through. I've had private conversations, and he is very kind and excited about other rockets in the industry when the cameras are off. So don't think of this as watching a rocket tour on the pad with a CEO of a company. Think about you being able to walk up to a really cool new rocket, and you're doing it with one of the smartest, most well-informed rocket nerds in the country. He's a nerd's nerd, and he's a really fun person to tour a rocket pad with. Another thing that makes this really special for me is my dad's gonna come along, and he's gonna help me by being the second camera guy. If you've seen my dad in previous videos, you know he's wicked smart. I mean, he loves building things, and he worked on the James Webb Space Telescope, so being able to share this with him is a very special thing for me. So let's go to Florida's Cape Canaveral Space Force Station. It's 2 days before launch. The only way we could fit this in for Tory is if we did it very early in the morning, so we found a patch of time right after sunrise, or during sunrise actually, and it's extremely windy. So it was a little difficult to record sound, but the reveal of the rocket is just incredible. So here we go. Let's go get smarter every day and go to the pad and learn about the Vulcan rocket. Okay, here we are before sunrise down in Florida. Check this out. That is pretty cool looking. Yeah, the lights make it look amazing. That's incredible. As we drove up on the Vulcan, I was just struck by how awesome this machine is. And to know that we had seen it being built in the factory, it's just incredible. As we drove up, we had to show someone our credentials, but I also want you to notice there's large lightning protection system towers all around the rocket. This is probably the best shot we're gonna get of that, so remember that for when Tory's talking about it later. Also, speaking of Tory, there's a guy around here somewhere with a cowboy hard hat on. We've just gotta find him. Hey Tory, oh, we're going mustache today.
Someone on the staff has to grow one, and no one stepped up.
So it's you. So this is Vulcan.
Mm-hmm.
Can we just go look?
Yeah, we can walk
I've never
right
seen
up
a
there.
BE4. I think I may have seen one at Decatur.
We can go right up underneath.
Can we really?
Yeah, I'll take you underneath the platform.
Let's do that.
Yeah,
Okay.
come on.
Sounds great. So they're gonna, you've got the patented Tory hard hat.
Yes, I do.
Okay,
Yeah.
I think at a certain point they're gonna make me wear a hard hat, right?
Yeah, once we get to the yellow line up there, we'll put a hard hat on you.
Okay, so before we go further here, can I just look at this? So we've got we've got the Vulcan here. Let me make sure my focus is working. So we have the Vulcan here. That cable over the top, that's the lightning protection system?
Yeah, so you see the 4 towers and the 2 sets of cables. That is the lightning protection system. And it's bigger than it looks. When you look at that inner square, it looks kind of tight, but it really isn't.
Really?
But that is the one thing that the astronauts tell me make them nervous. They feel like that's kind of feels small,
confinement?
But it's not. It will go right through the center of that.
Oh, that's amazing. Okay, and what is this tower over here? It's
all 4 towers. So the 4 towers are grounded, and then they're connected electrically to these cables that you see that surround the whole launch pad. So that whole thing is lightning protection.
okay.
This tower, that tower, that tower, that tower.
Got it.
It looks small, it's not. Everything's bigger than it looks because there's nothing around here to measure it by. That rocket's 202 feet tall, so that's 20 stories tall.
20 stories tall?
Yeah.
Okay.
And about 18 feet in diameter, 5.4 meters in diameter. Obviously, it's not fueled yet, okay, except for the solids. So we got 2 solids hanging there. Those are the GEM 63 XL, extra long, because they're about 7 feet longer than the GEM 63s we've been flying on Atlas so far.
What does the 63 mean?
63 inches in diameter was the original design of that original rocket motor that these are designed from. These are the longest monolithic rocket motors ever flown.
So they're not segmented?
Not segmented, one piece.
Which is good because you don't get cracks in the... I didn't know that. I thought these...
Yeah, so you don't have to seal them. There's no big O-ring joints like were on the shuttle segments or on Artemis solids. So it's a lot more weight efficient, so you don't have that big joint in there. And they're faster to make. It's 109,000 pounds of propellant in each one of them, so that's a lot of energy tied up in these guys. And all of that, 50 tons of propellant is expelled in less than 2 minutes, about 1 minute and 50 seconds.
And their thrust vector, the nozzles...
No, these are fixed nozzles because we have 2 BE4s on the liquid core, so that's enough control authority to get us all our pitch, yaw, and roll.
Really?
Yeah.
Okay, and so that's unique, isn't it? Because most solids, like on the ones you see on SLS and the ones you see on the shuttle, they were gimbaled, right?
Yes, they often are gimbaled, and when we have, when we flew the Delta with its solids, we had fixed or gimbaled depending on what we were doing and how many, and the same on Atlas. But for these, we don't need that. We got plenty of control authority on the liquid engines.
Okay. So weaseled Dad in here with me to do the B-roll, right?
Oh,
you can see the rocket?
I
That's
can
cool.
see it.
I think it's hard hat time.
Okay, got you.
Give me tight in the back.
I got it.
You got it?
All right.
All right, I got to get in a picture with you, Dad.
Okay.
Let's do that.
You worked James Webb, right?
I did, yes, sir.
Outstanding.
You can hold the camera down, Dad.
Okay.
Yeah, 1, 2, 3. That's great.
So you remember the gray part here? That's the MLP, or Mobile Launch Platform. You can see the 4 sets of rails.
There's rails here.
Yeah. So obviously, the rocket's not fueled with the liquid propellants when we move it out here, but the Mobile Launch Platform is still 2.5 million pounds. The rocket's like 100,000 pounds empty, plus the solids, which are 117,000 pounds each.
Well, is it pressurized? So
Only the upper stage.
Only the upper.
Yeah.
The Centaur is pressurized right now.
Right. Yeah, it has
Okay.
to be at all. You either have to have it stretched and supported mechanically or pressurized, because it's that very, very thin, as thin as 14 thou stainless steel. So it's a balloon tank. The first stage is rigid.
Okay.
So that's that orthogrid rigid aluminum structure that 2000 series structure you saw in the factory. So that's okay, but the upper stage has to be pressurized. And all of this was in the VIF behind you. The
Way
doors
back
are
there?
closed right now. Yeah, right there, we're ULA on the top.
Mm-hmm.
That's where we assembled all of this because it's too big to ship this way from Decatur. So the first stage, the upper stage, the payload fairing, the inner stage all come separately here on the rocket ship. They go to that building, we stack them vertically, then we bring in the solids, stack those, and then the last thing we do is bring in the fully encapsulated payload, in this case, Peregrine, underneath
Going to the
payload
moon.
fairing, going to the moon.
Which is cool.
Super cool.
That's awesome.
And then that gets stacked. It's all on top of the Mobile Launch Platform, so when it's all done, doors open, and it rolls out here at a blistering 2.5 miles per hour.
That's fun.
You know, it takes a couple hours to do it all because we come real slow to clear the building, and then we take off. You know, we're being careful. Somebody asked me the other day, they go, how long does it take to, roll from the VIF to the pad? And I said, about 8 years.
8 years. Yeah, it's a lot of time went into that, isn't it?
It was, yeah. Yeah, so if you go way, way up, the topmost one up there, that white one that looks bent, that's a flexible, what we call ECS, or Environmental Control System duct. That's air conditioning. That's for the payload. Temperature, humidity, stuff like that. Certain payloads, especially optical ones, you got to keep them super duper dry. And then below that, as you're going down, you've got umbilicals for the propellants. You've got umbilicals for all the electrical systems and the data and the power until we go to internal power. And then, of course, up there in the middle, you got a ground wind damper because it's a 20-story building.
That's a mechanical coupling there. Okay.
Right. Because, winds can get pretty high out here.
Today
it's supposed to. We're sway,
Here, how many hours out are we right now?
We're going to go at 2:18 in the morning on Monday, so we're ways out.
We're like 30-something hours out. Okay.
So that's ground wind damper, and then above that was all propellant and power and electricity and data.
I see.
And then as we come back down, then we've got, sort of more of the same.
Okay.
And then this is also different than what you're used to on Shuttle or even Artemis or even Delta IV Heavy, where we would have mechanical arms that would swing away when it's time to launch. These will disconnect and then sort of fall down out of the way, part of it passively, so that we don't have that complicated set of systems and hydraulics that we do like on a Delta IV Heavy.
How close can we go here?
We're gonna go until somebody stops us.
We're gonna go until somebody stops us. I like it. All right, I'm switching back to wide angle.
All right. So you remember the water suppression system?
Yes, that's for acoustics, correct?
For acoustics. So we call that the acoustic water suppression system. We're going to dump about, I guess we're going to dump about 10 swimming pools worth in the first minute here.
Okay.
And that's all about the acoustic energy that would come out of the rocket's exhaust and reflect off the ground. Water is almost the best, acoustic energy absorbing material you can have.
Okay.
And the reason that's important is because where we're standing right now, we'd be pushing 300 decibels. So if the fire didn't get us, the sound alone would just kill us right here.
Shake us apart.
Shake us apart. We get massive, brain hemorrhage, that kind of stuff.
Uh-huh.
But more importantly,
more importantly,
without all of that absorption, that energy would reflect right back on the rocket and likely damage the spacecraft.
Okay.
So that's what it's really about.
So can I walk over here to this side?
Yeah.
Boy, we're in a place right now. That's amazing.
Yes,
so
we are. So that rigid platform will go away.
This on the bottom goes away.
Yes, that grating you see, that goes away, and beneath us is the flame trench.
Okay.
And if you look to your right, that's the outlet to the flame trench right there.
All the fire goes that way.
Yep, and out of that thing and mows the lawn, knocks the fence over. But it's Florida, so the lawn will be back 5 minutes later.
Sounds great.
And so you can, those are the two BE4 engines, so we're going to get about 1.5 million pounds of thrust out of those.
Wow, they're grounded right now.
Grounded, yes.
All right, let me switch to my tighter lens. Okay, so GEM 63s, they're
GEM
canted.
63
they're
XL.
canted out.
Yeah, so that way we're getting the center of gravity from them through sort of the average center of gravity, because you know that for the rocket it's moving, because we're going to dump all that propellant in 5 minutes. That core will be empty. So we pick sort of the optimal place to pass the solids thrust vector through so that the BE4s don't have to fight too much of that on the way up.
I was surprised to find out that these solids are fixed and canted, because a lot of solids on big things like Shuttle and SLS, they have nozzles that move so you can do what's called thrust vector control, but they don't do that on the Vulcan, and why is pretty interesting. Look back at the bottom of the rocket. Those two silver things right in the middle, those are the BE4 liquid engines, oxygen and methane. If we think about what's going on here, you can actually move those. They have thrust vector control on the liquid engines, and what you can do with that is fascinating. You can vary the thrust, so you can like spin the vehicle in one way or the other. You can also, I'm going to shoot at you, you can also do things like this. You can, I mean, it's hard to describe, but you can see what I'm doing. You can even roll the vehicle by how you swing these bells around, which is fascinating. Now, the design choice they make, I think, is very elegant and very simple. They are thrusting the solids through the CG of the rocket. When you first start, if you look at the cross section of the rocket, you load up the liquids, you load up the solids. It's a very heavy rocket, and the CG is really high, though. It's towards the front of the solids, because you think about how long the rocket is, and you've got the Centaur upper stage, and it's fully loaded. So the CG is about here. But as you start burning and dumping mass out the back, the CG is going to slowly walk forward. That's fascinating. And so you would think, okay, well, if I'm a design engineer designing this system, I'm just going to average out and kind of shoot the middle of where the CG starts and where the CG ends, and that's where I'm going to thrust my solid rocket boosters through. And the reason they do that is because they don't want to overpower, so to speak, those liquid engines in the middle. If you are pushing through the CG of the vehicle, you're not trying to twist the vehicle and roll, pitch, or yaw or anything like that with your solids. You're just trying to add forward momentum to the vehicle. So that's how they do that. I think that's very clever. The fact that they've canted that, by the way, means if you have, let's say it's 3 degrees on the solids. If you have a sign of 3 degrees, that means you're pinching in with about 5% of your total solid rocket thrust, which means the design of the core has to be able to handle that compressive force, which I think is fascinating. And it's even more when you have 6 boosters on the outside of the Vulcan. I'm sorry, I'm geeking out right now, but this is a very complicated problem, and it's very interesting. Another thing to think about is when you're down at sea level, a 4-degree cant on your rocket is your rocket nozzles. That's going to twist the vehicle a certain amount, but when you get up 5 miles in the atmosphere, you've got less mass and you have less aerodynamic pressure. So that same cantover of the nozzles, you're going to get a much different response to the vehicle up at altitude. So they're probably not averaging that thrust spot to between the beginning and the end of the CG, because the response is different as you go up in altitude. They probably have an optimized spot, and that's where they're thrusting through, which I think is fascinating. It's a very simple, elegant solution to make these solids just a fixed nozzle at a certain angle, and it almost makes me empathize with the challenge that the guidance and control engineers have trying to figure out this control algorithm. But we're not going to do that, because those are guidance and control people, and everybody knows that solid propulsion and liquid propulsion people, that's where it's at. That's where the cool stuff is. I'm joking right now. Anyway, obviously, this is an amazing problem, and I'm excited just to hear Tori talk about it, because I'm learning, and I'm hoping you're learning too.
And so we'll get about 450,000 pounds of thrust out of each of those solids, plus the 1.1 million from the combined pair of BE4s. So this rocket, it'll weigh just under 1.5 million pounds fully fueled at liftoff. We'll have about 2 million pounds of thrust. So it's not going to leap off like if it had 6 solids. So you'll see it kind of, gently come off the pad and go.
Six solids, that's the maximum Vulcan handle.
Yeah.
Is that just a structural limit or just physical positioning?
It's physical space around the rocket.
Okay.
But obviously the structure's designed for that, because we knew that's what it would be. You don't want to waste any mass with extra structure.
So let me ask you about the BE4s. I know you wanted those things forever.
Yep.
It took a long time to get them to you.
It did.
You're excited you got them, right?
Excited we got them. We love them. They're good engines now that we got them.
So my understanding is, and don't let me hurt your feelings too much with this question,
all right.
Tori. My understanding is those things in testing, they've got a lot of horizontal firing time, but they don't have a lot of vertical. Like my understanding is 1 or 2 of them has like 4 seconds of vertical thrust time, right?
Yeah.
Real quick, this is what I was asking Tori. A horizontal rocket engine test is when you have a huge reaction mass and you horizontally mount that rocket engine up against that mass and you fire it and you measure thrust and pressures and flow rates and all that kind of stuff. A vertical test is when you hang the engine from your reaction mass like this, and you can test it in the configuration that it's going to launch. Typically, you want to do that because that's how the rocket's going to fly.
What's really more important than whether they're horizontal or vertical is how they interact with the rest of the rocket, because you're moving so much propellant through that thing. Remember, it's going to dump all of this, right? We got 86,000 pounds of LOX. We got 73,000 gallons, I said pounds, 86,000 gallons of LOX, 73,000 gallons of methane, all that's gone in 5 minutes. So the flow rate through these engines is humongous. And the orientation of the liquid rocket engine and its pumps really aren't a driving factor at all. What really matters is how it interacts with the rest of the rocket. And of course, that's the one thing you can't test until Monday morning when we really test it. So things like pogo interactions with the big fluid columns.
What does pogo mean?
Pogo is it's the tendency of a long fluid column to want to oscillate like an organ pipe, except with a with a liquid. And so that's one of the things we have to worry about with these big long liquid fueled space launch vehicles, because they're so big and they're so long. Is
it like water hammer over and over?
It's water hammer, right. So this thing is oscillating as we're flowing it through the pumps in the rocket engine, and we're throttling up and down. That fluid column wants to take all that energy and it wants to isolate or oscillate.
I see.
So we have pogo absorbing features in this design. That's the thing that you really got to test here on the rocket. How it interacts with the structure, which is another potential source, by the way, of combustion instability. You can have pogo where the feed to the pressure, the feed to the engines is oscillating because that fluid column is oscillating. You can get buzz where the engine is interacting with the structure and that's affecting the flow to the engine. You can get screech, we call.
What's it called?
Screech.
Screech.
Which is an acoustic phenomenon inside the combustion chamber of the engine, which was one of the problems we had to solve on this engine, because no one had successfully overcome screech in a large methane engine before.
At what kind of frequencies are we talking about?
Thousands of hertz.
Thousands of hertz.
Yeah, because
Okay.
it's a thing that happens right at the flame front, where you sprayed into this combustion chamber the LOX and the methane, and it's starting to combust, and you get these tiny little cells of combustion where it's mixed, and they're like little detonations. And so it's a tremendous amount of acoustic energy, and you can get standing waves transverse or radially inside that combustion chamber, not so much longitudinally, because the end of the chamber is open, that's where the gases come out, so there's nothing to reflect off of. But those other modes can get going in the thousands or tens of thousands of hertz, and if you let that happen, you can rip that combustion chamber apart in a second or two.
Really?
So that was part of what took a while to get the BE4s, was to solve that problem. And the way you deal with that screech problem in a combustion chamber is by carefully controlling your mixing,
Yes.
carefully controlling the pressures you operate at, but also by putting baffles and features in the faceplate of the injector to interrupt that resonance.
Just like the Apollo engineers did with the F1.
Exactly.
Right.
Yeah, this is not a phenomenon unique to methane. It was just particularly challenging for methane.
Why? Why is it harder than, say, kerosene?
Because
Paralox.
because of the chemistry of that combustion of the methane and oxygen. It just tends to be much more lively, if you will. So in that rough, rapid combustion zone, you can get a lot more acoustic energy generated instead of the energy going into heat and expansion.
Okay. Wow. Okay. So stoichiometrically, what are we looking at? Oxygen to
This is close to a 3-to-1 ratio.
Okay.
In practice, the stoichiometric ratio is always, ideally is always different than that, but you can't have 100% combustion efficiency. So, you can kind of back it out. I'm not going to tell you because it's proprietary, but you can kind of guess, because I told you how much propellant was in the LOX tank and the methane tank.
Yeah.
Right.
So do you use film cooling on these engines?
Yes. Yeah, that's part of it.
So
yeah.
film cooling is when you run it rich, I would
Yes.
say?
Yeah, this is an ox-rich engine.
Okay.
Yeah, so it's not a fuel-rich. We do use, fuel inside the bells to cool the bell and to cool the outside
Is
of the
this as
combustion
far as we can go
chamber.
toward the engine?
Yeah.
It's probably it. So let me
yeah.
zoom in real quick here. So I've got, that's Inconel, right?
Probably not supposed to tell you.
You're not supposed to tell me what that is. Okay, well, I'm an aerospace engineer and it looks like Inconel. So don't tell me. But I think I don't know, all I know is, I know there's been a lot of research into Inconel recently.
Yeah.
I do know that.
Yeah.
So that's
that's a very aerospace alloy Inco. That was for what, X15, right? So we could do our first.
Even the blankets on the F1, they use that, and so it's interesting. The reason I bring that up is because Inconel is very, very heavy. That looks like a heavy engine.
It's not a light engine.
Okay.
Yeah, I'll say that the weight is not too bad. It's obviously working fine in this application. And then there's a whole program that Blue Origin is involved in right now with us to continue to lower the weight of the engine and make it more structurally efficient.
I see. Because right now, looking at it, I can tell. I've researched it just a little bit. I'm not gonna pretend I haven't. So my understanding is back in the day with a lot of the Apollo engines, they would braze tubes in there.
Yes.
You would run the fuel up through the thing itself. This one is welded around the outside, is my understanding. You don't have to say if you're not allowed to.
Well, we can talk in general terms.
Let's talk in general terms.
Okay, so you don't use LOX to cool the combustion chamber or the bell because it's got poor heat transfer properties. You always use the fuel.
Oh, okay.
And that's also true here, even though it's not kerosene, and because it's just a better heat transfer element.
Is it the heat capacity or the heat transfer coefficient?
Both.
Okay.
So it is the thermal capacity as well as the conductivity of the fluid.
Okay.
And so when we look at like an upper stage engine like RL10, on this RL10 you would still see those brazed tubes, which is absolutely the most weight efficient way to circulate that coolant, like the radiator in your car. However, that is a handcrafted, craftsman, skilled guy bending little tubes, individually brazing them operation. So ultimately what you want to move to are machine channels or additively manufactured channels, even better yet, in order to, be almost as good, but a lot faster and a hell of a lot cheaper. And so this engine does not have little brazed tubes like an RL10 or like an F1. It's got channels. And even our RL10...
Rectangular.
Yes.
Interesting.
And even that upper stage, the RL10 that's, Airjet Rocketdyne, now L3, will move in our CX upgrade in a couple of years to that configuration, and we'll do away with those tubes. So it costs us a little bit of weight, but boy, we pick up a lot of speed and cost by making it that way.
3D printing?
Yes, 3D printing.
What's interesting about 3D printing is the surface finish of the metal.
Yeah.
And it'll create turbulence inside, and you want turbulence inside.
You do. So they're very good.
Yeah.
Very good, Destin. So I forgot about your fascination with laminar and turbulent flow.
That's right.
So as a matter of fact, we've been a little bit surprised. I'm not going to talk specifics about either engine, right?
Okay.
But we've been a little bit surprised as we have been developing that we get superior heat transfer and superior cooling conditions when we additively manufacture the channels that we didn't really expect. And it's largely due to that phenomenon.
The surface roughness.
Yeah, and so it's kind of offsetting a little bit the weight by getting better performance, because that affects performance, especially on an expander cycle like RL10, which is subject to the cube square limitation on how much thrust you can get out of it.
That's awesome.
Yeah.
I love talking to Tori. It's so good. It's so fun. So tell me about the red paint on the side.
Yeah, so
you gonna keep it up?
We'll do it every so often. So the next launch won't have it.
Okay.
Because we were kind of in a hurry to build that booster up, and it takes a little bit of time. We do this right now, we do this by hand. We take it in the paint booth and we mask it all off, and the guy gets in there and paints it. And it's not too bad, but it takes a little bit of time to do that. The weight's okay. For missions like this, we got plenty of extra weight. I mean, this is, that's less than a couple 100 pounds of paint on there. But going forward, we're looking at other ways to do it, maybe automated sprayers and things, so we can do it fast, and do it every time we have the weight margin to do it. So you'll see this like, every other one, every third one, we'll do the paint job on it.
That's awesome.
Because it's
good.
It's beautiful. But this mobile launch platform is deeper, this structure that you see right here.
Uh-huh.
And it's just a lot more ergonomically friendly. The one we have for Atlas, when you want to maintain all the piping and plumbing and data lines and stuff that's in the base, when you're on the Atlas one, you're laying on your back with a hatch, reaching up and you can't get up in there, and it's kind of awful. That thing is built so that we can walk around inside. It's like being in a submarine. There's
inside
hatches.
the thing, right here.
Yeah. If this were back in the VIF, we'd open a hatch and you could get in there and walk around and do stuff in there.
Is this new?
Yeah, this is brand new for Vulcan.
The whole thing is new?
Whole thing.
Oh, I didn't know that.
Yeah.
It was so cool to be this close to the rocket, but we had 2 days until launch, and all kinds of stuff happened before then. First thing that happened is Tori took time to explain to me how cryogenic fueling of rockets works. And that's so awesome that I'm going to make a whole video about that. Now, cryogenic refueling in orbit is going to be a big deal for the future of space exploration. So I first wanted to understand how you cryogenically fuel a rocket here on Earth in 1G. In order to see that, Tori actually let me go into the control room, and we learned about the sequence and how you do things. It's a complicated process, and I learned things I had no idea were even something to be concerned about. So I'm excited to show you that in a future video. If you want to see that, please consider subscribing to Smarter Every Day. I think you'll dig that. Some other cool things Dad and I did with our time. We went to the Visitor Center there at NASA's Kennedy Space Center. That was awesome. We saw the Atlantis space shuttle. That was incredible. We also got to do something that was really special for me in particular. When I was a kid, my dad took me to Disney's Epcot Center, and there's this one ride that has something to do with the figment of your imagination. There's this little dragon, and he goes around, and you're thinking about all your senses and all these types of things. I remember that with my dad when I was a child, and I really wanted to experience that with Dad now that I'm an adult. I just want to feel like a child again. So we did that. We rode this ride together, and it was really fun. It was just me and Dad just hanging out. It was awesome. I don't know why, but doing this with Dad made it that much more special. And when it came time to see the launch, I have never been this close to a large-scale rocket launch, and I've also never filmed one in slow motion. We did it this time. Before I show you that, I want to say thanks to today's sponsor. This episode of Smarter Every Day is sponsored by Factor. Now, Factor is a pretty cool service. They drop these meals off at your door, and they're not frozen. They come in this box that's insulated. It does have freezer packs in it, but it's just refrigerated. You open it up, and there's all these meals in there that are perfectly prepared, and it's like the convenience of what we've always called growing up TV dinners, only it's like you have a chef friend that drops you these meals. Let me show you how this works. Just pull this thing out, and the cool thing about it is that's not frozen. All you do is you get your sidearm, poke some holes, throw this thing in there. Let's go 2 minutes, which is like no time because it's not frozen. Do you play the game where you try to open the microwave on 0, or is that just me? Oh man, close. All right, here we go. Let's check this out. Woo! All right, that smells great. I've been working on my plating skills, and I would like to show you how good I am at this. Voila! Went from editing at a computer to eating creamy Parmesan chicken in 2 minutes flat. And this is the deal with Factor. They reached out and asked if they could sponsor Smarter Every Day. I was like, I'll try it. And it's amazing. Like, the food is legit off the chain. So if you want to check it out, go to factor75.com and use the promo code SMARTER50. That gets you 50% off your first thing and 20% off something else. There's so many things to think about. All I can think about is creamy Parmesan chicken. Hold on. All right, for real, this is what I'm supposed to tell you. Head to factor75.com or click the link below and use SMARTER50 to get 50% off your first Factor box and 20% off your month of orders. The convenience of grabbing these things out of the fridge and throwing it in the microwave for 2 minutes means you can get back to whatever it is you like to do faster. They've got all kinds of meals. They've got chicken, pork chop, turkey, vegetarian stuff if you want that. If you want to support Smarter Every Day, you want to try this, head to factor75.com or click the link below and use the code SMARTER50 to get 50% off your first Factor box and 20% off your month of orders. You're smart. You can tell when people are telling you the truth. I only work with sponsors I enjoy, and Factor meals taste great. So if you'd like to support the sponsor, that supports Smarter Every Day, and I'd be grateful. Thanks. The launch happened really early in the morning, like 2 a.m. early. We were very excited because I'd seen this thing being built, we had seen it on the launch pad, and we were together. Dad and I were driven across the base to a site about 5 miles away from the launch pad. There was basically nothing but water in between us and the rocket, so the view was amazing. There it is, way out there. We posted up and I got the high-speed camera ready and did my best to try to get focus set so we could capture liftoff. Here we go, right before launch. I've got a Phantom Miro right here, right at 1,000 frames per second. It meant a lot to watch this launch, and it meant even more because I was watching it with my dad. So is it possible for me to see when they tank the rocket? Can we figure something out where I can see how they do that?
No, we have a plan for you. In fact, I have personally selected a compliant screen for you to watch.
Oh, sounds great.